what I can. So Telco today will focus on shear strain localization, microstructural influences of small fatigue crack growth, and we studied that by using a digital image correlation and a novel EBSD technique developed by my co-authors. So we will see first a couple of slides on introduction and motivation, then we focus on methods, then we see results and discussion, then I will close my presentation. So when I worked my time at Alto, we worked a lot in close collaboration with shipyard industries, and there was quite a strong push to apply or to employ, let's say, high strength steel. And there were also many other applications where we noticed that the crack would spend most of the lifetime at the microstructural level. Therefore, for us, became quite important to tackle small or short fatigue crack interaction with microstructure and also all the other phenomena that happen at such a small scales. And we realized that maybe the limiting factor for further development in the field was the extraction, let's say, of a full field and a microstructural information at the crack tip. And we thought maybe the answer is in combining the digital image correlation and the EBSD technique. And we try to address a little bit of those topics in some previous papers, but we never really address the interaction of all these features. And therefore, in the workload today, the focus is to try to provide a better understanding of all the mechanisms behind the interaction of strain localization, microstructural features, and fatigue crack growth. We did that by basically tackle three big challenges: try to get an high resolution DSC, and we use an optimized speckled pattern. We will see an example. Then we try to get very high sample rate and very good crack growth detection. And then we employ a new EBSD technique developed by my co-authors called adaptive domain implementation approach. We won't see the details of all of this because it would be possible to fit 15 minutes, but you will see just, let's say, the main results. Let's say for the method, we realized we start from experimental test, of course, and we realized the double-edged notch samples you see here in the picture. We are talking about quite small samples, taking 1 millimeter, and they were made of ferritic stainless steel with the mechanical properties you see there in the slide. They were made via electrodischarge machining from an anneal plate, and the thermal the annealing process gave us an average grain size of 349 micrometers, so a little bit, let's say, larger than usual. Then we polished the sample to remove any damaged layer, and there was the notch radius, as you can see there in the picture. After the sample was ready, we introduced our pre-crack. In this case, we used uniaxial cyclic loading with a negative, slightly negative loading ratio. The problem was that we couldn't further improve the maximum stress due to the fact that it would have been too much high and too much close to the fatigue test, and therefore we decided to rely on negative loading ratio just because we wanted to realize the per crack in a reasonable amount of time. We need to check every few thousand cycles, and therefore it would become too much difficult otherwise. But we could obtain a per crack also with positive loading ratio. Then when we saw that we realized the physical true crack L stemming from the notch root, our sample was ready. The length was about 20 micron, to which, of course, you need to add the depth of the notch to obtain your full crack length. The most important aspect is that this crack is quite small compared to the average grain size, but is also long enough to avoid influence of the damaged layer from the EDM machine, which is about less than 10 micron from what we quantized via EBSD analysis. For the speckled pattern, all of you know very well that most of the time you use a random speckled patterns. The problem is that when you work with such a small scale samples, you want to really go there into details. The random speckled pattern doesn't provide really good information, and therefore we decided to employ an optimized speckled patterns. This was developed by the colleagues in Aalto University. You can see the ref in the slide. We don't go into detail, but basically it is optimized by minimizing an error function, which takes into account the correlation function you have in the DIC technique. And the pattern, therefore, is not sprayed, but is applied via silicon stamp. and then it's checked via optical microscope to see if the quality is okay or not. We can obtain a characteristic size of approximately 10 micron, where we can go even smaller from understanding from some recent tests that they did. Then we go to the testing. We realized load controlled fatigue testing with a loading ratio of zero point 0.1. We have a maximum stress of 350 megapascal, and we monitor the crack area with a digital camera. We have the resolution you can see here in the slides. We try to limit the field of view as much as we could and try to focus around the notch. We obtain a spatial resolution 1.76 micron per pixel. We detect a picture every 500 cycles, more or less in a 10 seconds break at 210 megapascal. And the first frame after 500 cycle was used as the reference. Then all the pictures were post-processed in LaVision, and in these experiments, I need to say we used only one camera, therefore we monitored one side. It was among the first tests we did, but in further tests, to further confirm our results, we also monitored the other side. So we implemented a double camera, we implemented automatic synchronized detection of picture and also crack length and so on. So it was a little bit more, let's say, interesting and complex. But in this case, we only monitor one side. Therefore, becomes very important, we will see later, to analyze also the fracture surface to see if our test is okay. When it comes to analysis of fatigue drag rate, we analyzes the pictures and we notice that every 2,500 cycle, we could see a reasonable increment of the crack length and the crack tip. And we reanalyzed the crack length we detected by using an incremental polynomial regression instead of using the direct second method. That's because when you have such very small increment of crack length, the error grows up exponentially if you use the direct second method when you try to make the derivative. And therefore, we use a polynomial regression as suggested by Standard, but also by many other authors. And it worked very well, as we will see later in the results. Then for the microstructure and domain analysis, this was quite extensive. We did EBSD technique analysis before fatigue testing, after fatigue testing, and also after final failure of the sample. We won't see all the details. Just want to underline that we use a so-called adaptive domain misorientation approach developed by my co-author, Pauli Lehto at Aalto University. And the characteristic is that it can resolve subgrains and dislocation cells, basically using measurement domains that are grown radially until a specified disorientation thresholds has been reached. And this gives us basically a way better resolutions and details. And then we can see some of the results. First of all, the fracture surface, since we monitored only one size, of course, we are sure we had a true pre-crack, but it's better to further verify that. First things, therefore, we checked was the pre-crack surface. As you can see in the picture A and C, it's quite flat. It's quite different compared to the other fracture surface, and that's because we had a different stress level when we did the fatigue testing and the pre-cracking operation. So we had a true pre-crack. There was no tunneling. This would otherwise create some trouble when we were doing the PSC reanalysis and all our assumptions, but in this case, everything was okay. Of course, there are asymmetries because we are dealing with the microstructural features, and that's unavoidable. But overall, I think the morphology is quite clear. Also want to underline that our reanalysis actually stops here because at a certain point, the crack had a deviation of 45 degrees from the, let's say, the direction perpendicular to apply load. And we decided that for our subsequent analysis, we would only consider fatigue rate until that point. But the specimen failed right after that. So anyway, it was reasonable. Overall, I think that the DSC characterizes well the near surface behavior, and maybe it could also approximate the interior of the sample, even though it's always challenging when we have this kind of phenomenon. And therefore, we can see the second results of my work, which basically is the small crack behavior. So in this picture, you can see overlay of the samples and the DSC reanalysis. For GB, we mean grain boundaries, and for LP are the strain localization points. So basically what we saw through the post-processing is that during the crack propagation, there were some areas where the strain localization, where the shear strain suddenly would start to increase steeply and then accumulates until another shear strain localization would form a little bit more far. So they were kind of following one after each other, let's say. And the characteristic was this steep change in shear deformation accumulation. This accumulation stage, we called it a transitional stage. Interestingly, this strain localization, they happen inside the grains. In one case, also the grain boundary, but they were always ahead of the crack tip. And we will see that later in the next slide. As I said before, everything after, let's say, GB3, so this here, was not considered in the subsequent reanalysis. And here comes the crack length. Here we can see very well that the strain localization points are always ahead of the crack tip and also how they position themselves towards the grain boundary. So if we hand this graph from, let's say, the x-axis, from the number of cycles via a number of cycles, we see that we have always the experimental crack length, which is below start or the stop of the shear localization. This means that when that localization is happening, the crack tip is behind. In some cases, it also happens, they are also getting different grain boundaries. For example, in this situation right here, we have a stray localization that is in the second grains, but the crack tip basically is still in the grain number one. Then we did analysis in terms of the fatigue crack rate to see how this stray localization would correlate to the retardation of the fatigue crack rate. So if you can see by using incremental polynomial regression, we have a kind of smoothened behavior of the fatigue crack rate. And we can see that why the grain boundaries can be found both at peak and valleys. When we check simply the retardation, we can always find a stray localization points. This is very clear on the right side. On the left side picture, the sub-picture A, we see instead how the crack is behaving during the transition stage. So on the right side, you have a physical correlation between crack tip and stray localization. On the left side, instead, it's just more a time correlation. So what's happening when the stray localization is developing, okay, but you don't have a physical correlations. And we saw that, as I said, the grain boundaries are both at peak and valley. So this may means that there isn't a direct effect maybe on the crack rate, but maybe there is an indirect effect because anyway we're talking about microstructural features which are expression anyway of grains and grain boundaries. We also noticed that there were different retardation magnitude, and we thought that maybe the grain boundaries would play a role in how the crack tip interacted with the strain localization that in our opinion were the main cause for those retardations. And that's where the EPSD analysis came into play. This is just an example, but basically we overlay our strain localization and CA images and also the grain substructure obtained by Michael Otto et al. And we can see that in those cases where the crack would penetrate the strain localization points, the retardation was very clear. And we noticed that in basically all the strain localization points, we had a lot of small dislocation cells and subgrains. This means that there was a local hardening due to this accumulation of plastic strain at the microstructural level. And therefore, it's quite an obstacle that the crack has to overcome if it were to further proceed. In other cases where the retardation was not so evident, instead, we noticed that the crack would try to change direction, and we found a lot of macroscopic cross slip, and the crack somehow avoided the stray localization, and in that case, as I said, the retardation was minor. Another aspect we notice is that distance and of course also the grain boundaries affects how the crack tip is interacting with the stray localization. What happens is that the grain boundaries act as a shield. So it's like if the crack tip is not seeing the stray localization, if there is a grain boundaries, they are shielding the effect. But then when the crack tip is reaching the stray localizations, it has only two choices, I told you before. bypass it through it, and then you have a very strong retardation, or try to overcome it if the slip system is favorable. And then in that case, the retardation is a little bit mitigated, basically. We had many other analyses when it comes to EBSD, but for the sake of brevity, they were not reported here. But we checked, for example, was checked if there was any effect on misorientation or the shielding or grain boundaries on the crack tip itself. And we saw that the retardation definitely did not dependent on the grain boundaries in this case, at least directly. We cannot claim that there isn't an effect in the end because their own expression is, as of the same microstructural situation. And a little bit wrapping up the main conclusions, we can say that the shear localizations in our experimental testing correlate well with the further rate retardation, while the grain boundaries can be found both in peaks and valleys. We can see that interaction between crack growth and shear stress localization depends on the relative distance and if there is a shield effect due to grain boundaries. Shear stress localization leads to the formation of grain substructure. This means that we have this location cell and subgrains, and these are local material hardened zones and are obstacles to the crack growth. If the crack tip penetrates directly the localization points, then the further crack rate retardation is significant and evident. Otherwise, basically, it is mitigated if it avoids the stray localization points. All additional details can be found in the references to see here, where we went a little bit further. As I say, we monitor as well the other side. We decide to analyze also the crack driving force, and you can find also more details on the EBSD aspect. And with this, I have conclude my work, but if there is any question, I'm always available.